Okay, now, we did this in the last class, but just to kind of review, put it in complete context. Because, one of you is doing differential equations, now you certainly understand the context, but not everybody is, okay? So, in case you're having any trouble with what we did, the idea here is that the rate at which some quantity changes is proportional to how much you've got. For example, if you got a tank full of guppies, not full, but a bunch of little fish in a tank, the more fish you got, the more new fish you're going to get. Okay, the more new fish you're going to get per day. Okay, so the rate of change of how many fish you have, which is y, is some multiple of y. Okay, like if you got 1,000 fish, then maybe you're going to get 10 new fish a day. And if you had 2,000 fish, you get 20 new fish a day. Okay, it means you multiply how many fish you got by some constant. And if you're getting 10 new fish a day for 1,000 fish, your constant would be 0.01. 1/100th of 1,000 is 10, right? So if you had 2,000 fish, you'd still have constant of 0.01. You get 20 new fish a day, okay? Well, that's the rate at which your fish population is changing. If it's money, it's getting compound interest, compounded continuously. Okay, if you got $1,000 in the bank, then maybe you're getting if T is measured in years, you got $1,000 in the bank. If your effective interest rate is 6%, then you have 0.06 times your $1,000. That's the rate at which your money is changing every year. Okay. So you want to, and if you're not really familiar with these examples, population and money, go back and review it. And, go to the OpenStax calculus book. It's free, it's online, or some other source. But that's the nature of exponential growth. When you have something that's changing at a rate that's proportional to how much you have, then you have this equation. And the solution to this equation is very simple. Just rearrange it, and I'm not going to go into detail about why you can treat these infinitesimal quantities as algebraic quantities. There's a little theory behind that, but there we have it, okay? You can do it, which gives you natural log of the absolute value of y equals kt plus a constant. Because of course you integrate both sides of this. So that absolute value of y is e to the kt plus c. C can be anything. So e to the c can be any number as long as it's positive. So instead of having an e to the c, I'm going to write a. Which is e to whatever your integration constant was. It's got to be greater than 0. Of course, this is the absolute value of y, so that y is plus or minus a e to the kt. Now, what's this have to do with physics? We talked about money, we talked about populations. Well, we're talking about capacitors. If you've got a capacitor in a circuit, then Y could be the charge. Okay, the voltage that you get here is proportional to how much charge you have. The potential difference is proportional to the charge. Now, we went over the details of that. I drew it out last time. So if you missed last time, you want to understand those details, but that's simple. The electric field of an infinite plate, and for points between these capacitor plates that are thought to be very close together, the electric field is pretty much constant between these two things. And you get the 4 pi k sigma thing. And so you know what the electric field is, you multiply that by the distance between these and you get the potential difference. And those are concepts that, of course, you want to be completely familiar with. You probably still have to think through them a little bit, but they're concepts that I've seen you use. And I think you're okay with it. So again, you're going to see it there. So the potential difference between these things is proportional to how much charge you got. Because of course, the sigma, your charge density on the surface of these plates is proportional to how much charge you got. You got more charge, you got more electric field, you got more potential difference, and it's directly proportional. So in this case, you got the potential difference equals, I'm going to use C for the capacitance. Potential difference across the capacitor plates is Q over C. If you have a resistor here, then the current is potential difference over the resistance. And that's Q over RC. I mean, potential difference is Q over C, and the current V over R. Then it's very clear that the current is I over RC. But your current, and again, go back to the explanation we did last time. Is the rate at which charge is flowing through this thing. Okay. And that's the rate at which the charge in the capacitor is changing, because if you just have a capacitor and a resistor, then where's the current coming from? It's coming from charge here trying to get over here, or charge here trying to get over here. Okay, you're reducing the charge in the capacitor by allowing it to flow through the resistor. And the current, well, you have all these relationships. You want to understand that whole picture. But what's this lead you to? The current is dq dt, but your current is also Q over RC. So dq dt is kq, where k is 1 over RC. In other words, it's just an instance of this, except it's y, it's q instead of y. So that's how capacitors behave. This is exponential. And actually, in this case, I've actually got it wrong. Well, it depends on your signs. And okay, so without talking about the signs and stuff, if the capacitor is discharging, then this is a negative Q over RC, okay? But if it's charging, then it's positive, and there are constants to be evaluated and initial conditions and stuff. And I went through the details last time, so just get it from the video. Thus, if K is positive, well, let's just say K is negative. I don't go through the details of that. How to get the other stuff. How do you apply this? It means you have a decreasing exponential, or maybe if you have a source in here, you have a slightly more complicated equation. Where this is Q and this is T, this line would be the voltage of the source. Now, what's capacitance? Capacitance is charge per volt. How much charge you get per unit of potential difference, right? Okay, so capacitance is Q over C, which means that C is what? I said it wrong. I said what I meant B. Okay. And you multiply the voltage by the capacitance to get the charge, because again, capacitance is charge per unit of volt. Okay, and I still haven't written this out right. I don't know what's going on. There's the equation, this, but in terms of intuition about what capacitance means, it's charge per unit of volt, per unit of potential difference, charge per volt. And if you multiply the charge per volt by the number of volts, you get the charge, right? So you have this, and then you have the curve. It looks like this. And all that comes out of what we did last time. So that's kind of a review of what we did last time. Get the details by looking at what we did in class previously. Now Zoom wants to reinstall itself, which is not necessarily a good thing you want to do when you have Zoom going. Okay, you got two capacitors, you got a source, and maybe you got a switch. Okay, you got a switch here, you close the switch. What happens? Okay, so it's like, just imagine you got a sheet of metal here, two sheets, opposing sheets close together, big sheets, side of the football field, side of the county, whatever. Okay, and you close the switch. Okay, and Oh, well, first, you got two sheets here and two sheets here. And they're connected by wires, and you got wires that go around to a battery or source of some kind. Okay. Now, what's that source going to do? Well, the potential of this sheet, the sheet here that's closest to the battery, is going to match the potential of the battery, because all you got between here and here is wire, and a wire is an equal potential thing. Ideal wire. Okay. Now there'll be a current, there'll be a little voltage loss in the wire, but we're going to consider the wires to be ideal, so there's no voltage loss. Okay. Now the other terminal of the wire is connected to the first sheet here. Okay. So you got the last sheet here and the first sheet here, and then you got two other sheets here that are facing each other. Well, this sheet is at the same potential as this terminal of the battery. This sheet is at the same potential as this terminal. So you're going to transfer some charge over, next microsecond, to transfer some charge from here to here or from here to here, depending. Okay. So these two plates are going to have the same charge, because where's the charge on this plate going to come from? It's going to come from this plate, or vice versa. There's going to be some transfer of charge, and these plates are going to end up with the same charge but opposite signs, equal and opposite charge. I should have said that the first time. Okay, so if you're taking electrons from here and charging and putting them over here, as would be the case if this is a positive terminal, electrons will be attracted to the positive terminal, repelled from the negative terminal. Okay. Then you got equal and opposite charges here, which means they're going to have equal and opposite charges here. Okay. So that at or there every instant. And it does take time for the charge to migrate. Basically, it takes time for the electric field to establish itself throughout these wires, okay? And that happens more or less at the speed of light. Well, that's really fast. So we say at, for all practical purposes, it's instantaneous. But if you're into really, really, really sophisticated, fast electronics, it can make a difference. It's the size of a computer chip. You do have a delay due to the speed of light. Okay, I'm not going to worry about that. At this point, I'm just reminding you that that can be a factor. Okay, so near every instant, or at every instant, effectively, in the ideal case, let's say that the charge on this one is equal and opposite to the charge on this one. Or the charge here is equal and opposite to the charge. Okay. So total charge is Q1 plus Q2. But that charge is equal to the voltage. Okay. Now, what I'm saying is quite right, because I guess we better have a resistor. Because you'll have a voltage drop across a resistor. So call that voltage the source minus voltage to the resistor. And that's going to equal the voltage on the capacitor. Okay, and I say, wait a minute, Q1 plus Q2 equals this. Q1 plus Q1. Okay, let me back up. Got to fix my notation. Okay, I'm going to come back to this because this is easier to understand. Okay. I should have started with this. It was kind of a bonehead thing. I started with this one. Because I was running into stuff. Well, okay, so we got voltage across the source, we got a voltage across the resistor. At any instant, the voltage across C1 is equal to the voltage across C2 because there's no potential difference in these wires. There's no voltage change through an ideal wire. So that I need a bigger picture because I really want to draw it more. Let me just quickly draw the picture. Capacitor here. Capacitor here. C1, C2. Now I've got a voltmeter. This voltmeter measures the voltage across this capacitor. And I've got another one up here, V2, another meter that measures the voltage across this capacitor. So here I got voltage to the source. And there's some voltage across the resistor. V1 is equal to V2 because there's nothing but ideal wire between here and here. And there's nothing but ideal wire between here and here. So now, remember again, and it helps to write this out, the capacitance is the charge over the voltage. So you don't get confused, okay? And so I don't get confused and write this wrong, which I did last time when I was developing the whole thing. Okay, so the voltage is what? It's a Q over C, right? So Q1 over C1 equals Q2 over C2. Now, the other thing I'm going to do, well, the total charge, we'll get to that. Okay, I'm just going to call the common voltage, V1 and V2. I'm just going to call that V. Okay, so total charge over the combination. Total charge over that parallel combination is And the potential is Q1 plus Q2, because you got so much charge here and so much charge here. And think about, this thing has pulled negative charge off of here and negative charge off of here, so that the voltages adjust to be the same. I want to think through that. Don't want to say too much more about that. The potential difference is V. So the capacitance, all this Q total, is Q total over V. But Q1 over C1 equals Q2 over C2 equals V. And Q1 is C1V1. So C2V plus, okay, Q1 is C1 times V, Q2 is C2 times V. Because V is the common voltage. Voltages are the same, so we can do this. That just equals C1 plus C2. So a parallel combination of capacitors just sums up the capacitance. If you think back now, I can't really gesture with parallel combination. It's as if these two plates are added to one plate. If you melt these two plates into one plate and melt these two plates into one plate, it's equivalent to just circuit with just that one capacitor. Okay. These plates are the size of a football field, and these plates are size of a tennis court. It's equivalent to having just one plate here and one plate here, both the size, each the size of a football field plus a tennis court. Okay. And it's because the charge is being pulled, well, the voltage across each is the same. Okay. So whatever charge you're pulling off of this one, whatever charge you're pulling off of this one, is the same charge you'd be pulling, same total charge you'd be pulling if these two were combined. That's what it comes down to. Okay. Now over here, where here you have equal voltages, here you have equal charges. Okay. Again, another reason you have total charges is there can't be any net charge between this plate and this plate. You have to have a gap before you can separate charge. The reason for that is if you locate even 1 coulomb of charge between here and here, remember what it means to have a coulomb sitting there smiling at you. Okay, it creates a huge electric field. Now you can create a huge electric field across this gap, but you can't create a huge electric field here in your room. Okay, and you can't create a huge electric field here. Okay, the electric field has to be between here and here, between here and here. Another way of saying it is you got zero electric field in any continuous conductor. Okay, well, let's see where we are real quickly. Okay, I wrote down Q1 equals Q2, which is or Q1 plus Q2, Q1 equals Q2. And Q1 equals Q2, we're going to call that Q. V1 plus V2, then is what? Well, voltage is Q over C. We're going to call that the total voltage. Whenever these capacitors are charged, they have some total voltage. It's related to the voltage of the source and the voltage of the resistor. Okay. Then we want to include that to get the total picture, but at any instant, you got some total voltage. I'm being really careless today. Same equation, but V1 is equal to Q1 is equal to Q2. So that your total voltage is Q over C1 plus Q over C2. So that your net capacitance is the charge over your total voltage. So it's this. You divide out the Q. This just comes out 1 over C1 plus 1 over C2. So leave myself room. So 1 over the net capacitance is 1 over C1 plus 1 over C.